Normal distribution. The probability distribution known as normal distribution is, by the amount of phenomena that explain, the most important of the statistical distribution. To the normal distribution, also called it with the name of the campaign of Gauss, as representing the probability function is bell-shaped. The normal distribution was studied by Gauss. It is a continuous random variable. Variable can take any real value. The density function is bell-shaped. Two parameters determine a normal distribution, the mean and the typical deviation. The normal distribution is of vital importance in statistics for two main reasons. Number one, many continuous phenomena seem to follow a rule can be approximated by this. Number two, we can use it to approximate various discrete probability distributions and avoid the heavy calculation. The normal distribution has several important theoretical properties listed. Number one, it has a bell-shaped and is symmetrical in appearance. Number two, their measurement of central tendency, mean, median, mode, median range, and median axis are all identical. Number three, its associated random variable has an infinite range. This is a normal curved bell of Gauss. Mean, median, mode. The left end extends indefinitely but never touches the horizontal axis. The normal distribution of probability is symmetrical around a vertical line erected on the mean. The right end extends indefinitely but never touches the horizontal axis.
Areas under the normal curve. No matter whatever the values of mu and sigma for a normal probability distribution, the total area under the normal curve will be 1.0. And we can consider that the areas under the curve are probabilities. In mathematical terms, it is true that approximating 68 forms of all the values in normally distributed population are within one standard deviation with positive and negative signs with respect to measure. Use of standard normally probability distribution table. We can show the area under the normal curve between the mean and any value of the random variable with a normal distribution. Note, in the table, the column's location denotes receive values derived from the formula. C is equal x plus mu between sigma. X is equal values of the random variable. Mu is equal mean of the distribution of the random variable. Sigma is equal standard deviation of the distribution. C is equal number of standard deviation of x with respect to the mean of the distribution. Example. We have a training program designed to improve the skill of the work of the production. The program is self-applicable and that operators require a different number of hours to finish. Study of previous participants revealed that the average time devoted to the program is 500 hours and that its random variable distribution normally has a standard deviation of 100 hours.
Letter A. What is the probability that a select participant randomly takes more than 500 hours to complete the program? In this case, we divide 500 between 100, so C is equal to 0.5. Now, we are looking for the table value. We can see that 0.5 is equal to 0.1916. Letter B. What is the probability that a select participant randomly takes between 500 and 650 hours to finish the training program? So, we have represented this situation graphically in Figure 2. The probability that answers this question is represented by the sharing area between the apples, 500 hours, and the value of x we are interested in. Applying the equation, we calculate a value C. So, C is equal to x, in this case 660, less mu, that is 500, between sigma, that is equal to 100. To try in the numerator, we have 150 between 100, so C is equal to 1.5. If we calculate C equal 1.5 in the table, we find a probability of 0.4332. So the probability that a select candidate randomly takes between 500 and 650 hours to finish the training program is slightly more than 4. Letter C. What is the probability that a select participant randomly takes more than 700 hours to complete the program? This situation is different from the previous example. Let's look carefully at figures. We are interested in the sharing area to the range of the value 700 hours. So, how can we solve this problem? We will start using the equation. C is equal to x, in this case 700 less mu, that is 500, between sigma, that is equal to 100. Trying the numerator, we have 200 between 100, so C is equal to. If we go to the table for a C value, we will have a probability of 0.4772. That figure represents the probability that the program requires between 500 and 700 hours. However, we want to know the probability that takes more than 700 hours. Given that the right half of the curve represents a probability of 0.5, we will get the answer if we subtract 0.5 less 0.4772, which is equal to 0.0228. Therefore, we are exactly 2 probabilities in 100 that a participant should at random takes more than 700 hours to complete the course. Letter D. What is the probability that a select participant randomly takes between 420 and 570 hours to complete the program? The figure shows the range of 420 to 570 hours. Also, in this case, the solution requires 2 steps. First, we calculate the C value for the point of 570 hours. C is equal to x, in this case 570, less mu, that is 500, between sigma, that is equal to 100. Subtracting the denominator, we have 17 between 100, so C is equal to 0.6. We are looking for the C value in the table, and we get a probability value of 0.2580. Second, we calculate the C-value for the point of 420 hours. C is equal to X, in this case 420, let mu that is 500, between sigma that is equal to 100. To try in the numerator, we have minus 80 between 100, so C is equal to minus 0.8. Since the distribution is symmetric, we can ignore the sign and look up the C-value of A. The probability associated with this last is 0.2881. We find the answer by adding the two values. So, 0.2580 is the probability that the random variable is between the average and 520 hours. 0.2881 is the probability that the random variable is between the average and 420 hours. And 0.6461 is the probability that the random variable is between 420 and 570 hours. So, there is a little more than 50% chance that a participant should at random stay between 420 and 570 hours to finish the training program.